Okay, let's look at what's called the Pythagorean Theorem, which tells you how the lengths of a right triangle's three sides are related. And by right triangle, we mean a triangle with a right, or 90-degree, angle. Suppose this right triangle has side lengths A, B, and C. If you already know the Pythagorean theorem, then what's c squared in terms of A and B? If you're not sure, then click down here and we'll figure it out together. Excellent! You already know that for this right triangle here, c squared equals a squared plus b squared. For any right triangle, the square of its hypotenuse equals the sum of the squares of the two legs. If you want to prove the Pythagorean theorem, click over here, and if you'd prefer to just see a few examples, click here instead. Okay, great. Now to prove the Pythagorean theorem, let's first take our right triangle here, and let's make a few more copies of it. And we've arranged these triangles so that they form a big square. Also, if we look carefully at the region inside these triangles, we have another square whose four sides are the hypotenuses of our right triangles. So what's the area of this green square? Remember, its sides have length c. Nicely done. So the area of this green square is c squared. Next, let's take a piece of this green square and move it. We're going to move this triangular piece down here and move it so it's on top of this yellow triangle on the left. So what's the total area of the green region now? Don't worry, this is not a trick question. Precisely, we've only moved a piece around, so the green region still has an area of c squared. Next, let's move this triangular piece over here so that it's on top of the yellow triangle up here. Now the area of the green region is still c squared, but let's find another expression for the green area. We'll do that by drawing in a line over here. Notice that we've split the green region up into two squares. This top square has side length A, and this bottom square has side length B. So in terms of A and B, what's the total area of this green region? Excellent work! This top square has an area of a squared, and this bottom square has an area of b squared. So by rearranging a few pieces of the green region, you found that its total area is a squared plus b squared. And so we found two expressions for the area of the green region, so these two expressions must be equal. In other words, c squared equals a squared plus b squared. And this relation is called the Pythagorean theorem. It's only true for right triangles, and it says that if you square the hypotenuse, then that's equal to the sum of the squares of the two legs. So we have a formula for finding c squared. But what's the length of this triangle's hypotenuse, c, in terms of the legs a and b? You can take the square root of both sides of this equation to find out. Right. To solve for the hypotenuse c, you can take the square root of both sides of this equation. On the left side, the square root cancels the square, leaving us with c equals the square root of a squared plus b squared. So in a right triangle, the hypotenuse always equals the square root of the sum of the squares of the two legs. Next, let's see some numerical examples. Suppose you have a right triangle, and its two legs have lengths of 8 and 15. What's the length of its hypotenuse? Try using the Pythagorean theorem to figure it out, and you can use this interactive right triangle to check your answer. So when the legs of a right triangle have lengths of 8 and 15, the hypotenuse has a length of exactly 17, because 8 squared plus 15 squared equals 17 squared. For this example, the numbers worked out really nicely, and all three sides had lengths that are whole numbers. But it won't always work out so nicely. For example, find the hypotenuse of a triangle whose legs have length 7 and 10. Feel free to use the interactive right triangle to get a sense of what your answer should be, but try coming up with the exact answer, which will have a square root in it somewhere. Right, when the legs are 10 and 7, it looks like the hypotenuse is about 12.2. If we apply the Pythagorean theorem, we find that 10 squared plus 7 squared is 149, which means the exact length of the hypotenuse is the square root of 149. Sure enough, that's about 12.2. Next, Suppose you have a right triangle where the hypotenuse is 15 and one of the legs is 9. How long is the other leg of the triangle? Nicely done. If you call the missing leg b, then 9 squared plus b squared equals 15 squared. To solve for b, you can first subtract 9 squared from both sides, giving you b squared equals 15 squared minus 9 squared, which equals 144. So b is the square root of 144, or 12. And sure enough, that's exactly the side length you get from the interactive triangle as well. So you can use the Pythagorean theorem, a squared plus b squared equals c squared, to solve for the hypotenuse when you know the two legs, and you can also use it to solve for one of the legs when you know the other leg and the hypotenuse. Try another example. If a triangle's hypotenuse is 17 and one of the legs is 10, how long is the other leg of the triangle? Again, try coming up with the exact answer, which will have a square root in it somewhere. Now let's finish off the Pythagorean theorem with a practical example. Suppose a fire truck is parked 70 feet from a building and you want to extend the ladder 240 feet vertically up the building. How long does the ladder need to be so that it reaches the top of the building? Here we'll introduce what are called Pythagorean triples. But first, let's make sure you remember the Pythagorean theorem. Suppose you have a right triangle and its legs have lengths of 7 and 10. How long is this right triangle's hypotenuse? Your answer should have a square root in it. And if you'd like to review the Pythagorean theorem instead, click down here. Exactly. The hypotenuse of this right triangle is the square root of 10 squared plus 7 squared, so that's the square root of 149, or about 12.2. Next, try finding the hypotenuse of a smaller right triangle whose legs have lengths of 3 and 4. The numbers for this triangle will work out a little more nicely. Nicely done. The hypotenuse of this right triangle is 5, because 3 squared plus 4 squared equals 5 squared. So unlike that earlier triangle with the square root, this is a right triangle whose sides are all whole numbers. So 3, 4, and 5 are what's called a Pythagorean triple. They're 3 whole numbers that are side lengths of a right triangle. Let's find some more Pythagorean triples. One way to find more triples is to start with a triple, like 3, 4, 5, and to make the right triangle bigger or smaller. Let's make another right triangle whose side lengths are all twice as long, so this side here is 6, and a third triangle whose sides are all 3 times longer, so this side over here is 9. Using the fact that these 3 triangles are all similar, try finding the remaining side lengths for these larger right triangles. Excellent. So you've discovered 2 more Pythagorean triples, 6, 8, 10, and 9, 12, 15. We could keep making larger and larger similar triangles, but for now, let's look for some Pythagorean triples that are not just multiples of 3, 4, 5. Here's a right triangle with a different shape, and suppose this leg has length 5, while this leg has length 12. How long is this triangle's hypotenuse? Precisely, this hypotenuse is 13, so 5, 12, 13 is another Pythagorean triple. Let's look at one more. Here's a right triangle with legs of length 8 and 15. What's the hypotenuse of this triangle? Nicely done. This hypotenuse is 17. It turns out that there are infinitely many Pythagorean triples, and there are ways to quickly find them. But let's save all that for another lesson. To finish this lesson off, try finding the missing hypotenuses for these 4 Pythagorean triples. And this last one just might be a multiple of a Pythagorean triple you found earlier.